Well, hello. Here's a video that deals with doing a hypothesis test on a mean when sigma is unknown. Again, sigma is the population standard deviation, and so this is the more realistic setting, not knowing the population standard deviation and trying to perform a test on the population mean. Okay. An automobile manufacturer claims that their car has 51.3 miles per gallon. Whoa, pretty good here. An independent testing firm has been contracted to test the miles per gallon for this car. After testing 12 cars, they found a mean miles per gallon of 51.6 with a standard deviation of 2 miles per gallon. Is there sufficient evidence at the 0.01 level that the cars outperform the manufacturer's miles per gallon rating? We may assume that the population is normally distributed. Okay, so what we want to do here is first, in this setting for this problem, I want to identify the parameter of interest, which is a mean here. This is the parameter of interest. Mu, the population mean. This is the mean miles per gallon of all cars of this type. That is, this particular car that the manufacturer claims has this miles per gallon rating. And I want to say something about this, okay? I want to say something about mu. In particular, I want to say something about it through a hypothesis. The question being asked here, is there sufficient evidence at this level that the cars outperform the manufacturer's miles per gallon rating? Well, the car would outperform the rating if mu was greater than 51.3. That's the rating of the manufacturer. That's the claim we want to test. Again, we put the claim that we want to test in the alternative hypothesis. So that's the alternative hypothesis. The null then is the competing hypothesis, and it's that mu is less than or equal to 51.3. Mu is unknown. We want to test this idea. Is this hypothesis true or not? Okay. A little bit more information I want to gather before I go on to step 2. From my sample, I noticed that we looked at 12 cars, and from the sample, the average mile per gallon of those 12 cars was 51.6, and the standard deviation of the miles per gallon for those cars was 2. Now this is not sigma, this is S. S is, if you recall, the sample standard deviation. So for my sample information, I have this here. Okay, so now the question is, which test statistic do I use? Well, step 2 gives me a hint that I'm going to use the t-test statistic, but let me just kind of give a bit of a review here. You recall that the test statistics that we have so far are x bar minus mu over sigma over root n, or z equals x bar minus mu over s over the square root of n, or t is x bar minus mu over s over the square root of n. Let me go ahead and put naught here. The mu naught, as you recall, is the fixed value of the population mean under the null hypothesis. That is, when I assume the null hypothesis is true, I'll plug in mu naught for what would usually be a mu here. Okay, now if you recall, this test statistic is used when I know sigma and my sample size is large, bigger than 30, or my population is normal. Well, I don't know sigma in this problem, so I'm not going to use this test statistic. This test statistic here is used if my sample size is greater than or equal to 30. which I don't know, which I don't have here. My sample size is 12, so I'm not going to use this one. This t statistic, called the t-test statistic, is used if I have a small sample size, sigma is unknown, but I need the requirement that my population is normal. And while I've got that here, we assume that the population is normally distributed. What we mean is that all mile per gallon ratings for all cars of this type follows a normal distribution. And if that's the case, then this ratio follows the t-distribution. And you recall here, the degrees of freedom for the t-distribution is n minus 1. So the degrees of freedom for this problem is 12 minus 1, or 11. Okay, so we're using the t-test statistic. So what's the value of it? So we have t equals x bar minus mu naught over s over the square root of n. And so x bar here is 51.6 minus mu naught. Again, mu naught is the value I choose under the null hypothesis, or the value of mu under the null hypothesis. Well, the null hypothesis says that mu is less than or equal to 51.3. And in this context, or this kind of problem, we put mu naught at 51.3. That is the largest that mu can be, and the null hypothesis still be true. And so I'm picking the most conservative value of mu to plug in for the null for this placeholder here, and still be true under the null hypothesis. S is 2 divided by the square root of 12. And so if I do this computation here, you can work through it, but you get 0.52. Okay, so this is my test statistic value, 0.52. Recall the test statistic is evidence against the null hypothesis. It's the evidence from the data. Okay, is this a one-tail test or a two-tail test? Well, let's see here. That comes back to, what does my alternative hypothesis look like? The alternative here is that mu is greater than 51.3. In fact, I can, using that information, I can actually draw out the rejection region here, or sometimes called the critical region. The rejection region, or the critical region, is based on the distribution of my test statistic. I have a t-test statistic, so my rejection region is on or comes into play with the t-distribution. The t-distribution has a mean of 0, as you recall. Now, it's a one-tailed test because in the alternative I have mu is greater than some value. And because it's greater than, it's a right-tailed test. So I have right here a t sub alpha, comma, the degrees of freedom. And the area under the curve to the right of this t value is going to be whatever my alpha is. And the alpha, if you recall, specified was 0.01. That means that I'm willing to make a type 1 error with probability 0.01. Okay, so let's see here. What's my degrees of freedom? Degrees of freedom is 11, so I'm really looking at t sub 0.01 comma 11 degrees of freedom. Well, I have to get this critical value from the table that has the t-distribution on it. Okay, and so looking at your table here, I'm going to pull out the table. Here I've got degrees of freedom at 11, and I'm looking at t sub 0.01. So I scroll over here, t sub 0.01. The t critical value is 2.718. Okay, so 2.718. And everything to the right of this value is my rejection region. Okay. Now, so back to step 3. We've done a lot of work here, but from the setting up the rejection region, we can see that this is a one-tailed test. Okay, step 4 says enter the decision rule. This is kind of small here, but this says reject H naught if T is greater than some value, or from my picture here, that value is 2.718. That is the critical value. What I'm saying here is if my test statistic is quote unquote large enough being in this portion of the tail, then I'm going to conclude that I have sufficient evidence to reject this notion that mu is less than or equal to 51.3 and accept the idea that mu is greater than 51.3. Okay, so coming to step 5 here, and what's my conclusion? Well, my test statistic is 0.52. That does not, from the decision rule, I would not reject because clearly 0.52 is not bigger than 2.718. So in this problem, I'm going to fail to reject the null hypothesis. And what that means for us is if we come back to the context of the problem, that means that, well, we don't have evidence to conclude that this is not true. In other words, or we don't have evidence to say that, on the other hand, that mu is bigger than 51.3. It's kind of our results are inconclusive. We can't say one way or the other from our data. So that's where you would stop with this problem. Okay, I say that's where you would stop with this problem. If you wanted to go a little bit further, you could actually use the same data here and use this formula, x bar plus or minus t sub alpha over 2 times s over root n, the t interval, and you could estimate mu with a confidence interval. And that might give you an idea of where this mean mile per gallon of all cars of this type lies. That would be of interest for this manufacturer. Okay, I hope this was helpful.